Hey fellow nerds, today we are going to discuss half-wave rectifier. We will start with average and RMS values of AC voltage and current, then move on to need for rectification, half-wave rectifier, peak inverse voltage, half-wave rectifier with smoothening capacitor, half-wave rectifier with capacitor and load. When electricity is generated in power plants, it is produced as alternating current. It is constantly changing its direction, forming a sinusoidal wave that rises and falls as it travels. This sinusoidally varying current or voltage is very useful for us because it is efficient for long distance transmission since we can step up its voltage for reduced loss across the power lines and step it back down for safe use simply by using transformers. Let us take a sinusoidally varying voltage and find its average value over one time period. Here the maximum value of the voltage is V naught and it is sinusoidally varying. So mathematically we can write it as V naught sine omega t. Average value of a time varying voltage is given like this. V average is integral from 0 to 1 time period V dt divided by integral from 0 to 1 time period dt. So on the numerator, this becomes integral from 0 to t. V is V naught sine omega t dt divided by integral from 0 to t dt. Integral dt is t, giving the limits from 0 to t. This is simply t minus 0 or t. Let us replace it by that. On the numerator, we have integral V naught sine omega t, but V naught is a constant, we can take it out of the integration. So this becomes V naught divided by t, integral from 0 to 1 time period of sine omega t dt. Now, integration gives you the area under the graph. And sine omega t in one time period looks like this. It has equal positive area and negative area under the graph in one time period. So if you take the integration of sine omega t across one time period, you simply get 0. So the average value is 0. The reason for the result is that the area under the graph in one cycle is 0. Turns out that the average value of AC voltage or current over one full cycle is 0. It is clearly not useful for us to understand its actual power capacity. To solve this, we need a better measure, one that captures its actual effective power. That is why we have the RMS value. RMS stands for root mean square. We square the waveform first so that all the negative area will become positive. Then we find the mean and later to nullify the squaring effect we take the root. The first step is to square our waveform. We get V square as V naught square sine square omega t. V naught sine omega t is sinusoidally varying. If we square it, the waveform will look like this. All the area under the graph is positive now, so if we take the mean, it will not come to be 0. So as the next step, let us find the mean. Like we saw previously, mean of any quantity x is given like this. Integral from 0 to 1 time period of x dt divided by integral from 0 to 1 time period dt. Here x or the quantity whose mean has to be found is v squared. V squared is V naught square sine square omega t. So the mean will be integral from 0 to 1 time period of V naught square sine square omega t dt divided by integral from 0 to t dt. In the denominator, we have integral from 0 to t dt. Integral dt is just t. Giving the limits from 0 to t, we get it is simply t. Let us replace it by that. On the numerator, v naught square is a constant. Let us take it out of the integration. So this is basically v naught square by t multiplied by integral of sine square omega t dt across one time period. Let's try to find what is integral of sine square omega t across one time period. For that, we need to use a trigonometric relation. Sine square omega t is 1 minus cos 2 omega t divided by 2. So here we can write integral from 0 to t of 1 minus cos 2 omega t divided by 2 dt. We can split this into two integral of 1 by 2 dt and integral of cos 2 omega t by 2 dt. 1 by 2 is a constant. Let us take it out of the integration. Here again we have integral of dt from 0 to t. It is t. Let us replace it by that. In the next term we have to integrate cos of 2 omega t divided by 2 across one time period. Just like a sine function, a cos function also has equal positive and negative area under the graph in one time period. So if you integrate it, you're basically adding these areas and you will get this is equal to 0. So this is simply t divided by 2. So we get the mean value of v square. It is v naught square by t multiplied by t by 2. T and t gets cancelled. We get v naught square divided by 2. The third step to find the RMS value is to take the root. So v RMS is going to be root of v naught square divided by 2, or v RMS is v naught divided by root 2. RMS value of a sinusoidally varying quantity is its peak value divided by root 2. RMS value lets us know the effective power of alternating current or voltage. Now, since AC power is efficient for transmission over long distances, because of how we can step it up and down using transformers, power is commonly supplied as AC. However, most electronic devices that we use, like your laptop, your mobile phone, they require a stable DC power source to operate properly. They cannot stand the power source being altered. They cannot handle the constant fluctuations of AC. They need a steady one directional flow of current, like DC. This is why we need rectification. Rectification is the process of converting AC to DC. It transforms an oscillating current into a steady unidirectional current that our devices can safely use. What an ideal rectifier would do is this. It will take a fluctuating AC input and convert it into a steady unidirectional DC output. Let us start by taking a simple circuit with a resistor and a diode. Input is given over here and output is taken across the resistor. I am going to give a sinusoidal input to it. To plot the output, let us take one more graph. In the first half cycle, the input is positive. So the diode gets positive voltage here and negative voltage here. So the diode will be in forward bias. If we take the ideal diode model, we can replace it by a closed circuit. So for 0 less than t by 2, the circuit model will look like this. Whatever is given in the output will be exactly seen across the resistor. So V output is going to be equal to V input. Let us plot it on the graph. The same thing will happen in every positive half cycle. So let us plot the same over here also. Now, in the negative half cycle, the diode will get negative voltage here and positive here. It is reverse biased. Since we are taking the ideal diode model, it can be replaced as an open circuit in the circuit model. So for t by 2 less than t, the circuit model will look like this. Since the circuit is open over here, no current will pass through the resistor. According to Ohm's law, the voltage across the resistor will be 0, but our output is taken across the resistor, so output is also going to be 0. Let us plot it on the graph. So this is how the output looks like when we take the ideal diode model. What I can see is all the negative half cycles of the input has been rectified or corrected. Or we can say the rectifier has rectified one half cycle of the wave. Because of that, this circuit is called a half-wave rectifier. So this is how the output of a half-wave rectifier looks like if we take the ideal diode model. How about now we try to plot the input-output characteristics? We saw that for V input being less than 0, V output is simply equal to 0. For V input being greater than 0, V output is exactly equal to V input. We want to plot V output versus V input, taking V output on the y-axis and V input on the x-axis. When the input is negative, output is 0. That means the slope of the graph, which is V output divided by V input, will be 0. We can plot it on the graph like this. Again, when V input is positive, V output is equal to V input. The slope V output divided by V input will be 1. So we get a straight line whose slope is 1. Let us try to find the average value of this output. We know the equation to find the average value of any quantity. Here we want to find the average value of the output voltage. So V average is integral from 0 to 1 time period of V dt divided by integral from 0 to 1 time period of dt. We have to integrate the voltage from 0 to 1 time period. For the first half of the cycle, we have the sine wave. For the next half, we have 0. So we don't really have to integrate from t by 2 to t because the value is 0 anyways. We have to integrate from 0 to t by 2. From 0 to t by 2, output voltage is equal to input voltage, which is V naught sine omega t. So the numerator becomes integral from 0 to t by 2 of V naught sine omega t dt divided by, in the denominator again we have integral from 0 to t dt, which is t. V naught is a constant, let us take it out of the integration. Now this is V naught divided by t. Integral of sine omega t is minus 1 by omega cos omega t. We have to give the limit from 0 to t by 2. So we get minus V naught by t omega. Giving the upper limit, we get cos of omega t by 2 minus giving the lower limit cos of 0. Now we know omega is 2 pi by t. So omega t divided by 2 will be pi. Over here we need cos of omega t by 2. It is simply cos of pi. Since omega is 2 pi by t, t multiplied by omega is 2 pi. Now minus V naught divided by 2 pi, cos of pi is minus 1, minus cos of 0 is 1. Minus 1 becomes minus 2. Minus and minus can be cancelled. 2 and 2 can be cancelled. So this becomes V naught divided by pi. The average value can also be called DC value. So we can write VDC is equal to peak value divided by pi. 1 by pi is 0.318. So we can write the average or the DC value is 0.318 times V naught. Let us now do the same analysis by taking the constant voltage model of a diode. In the positive half cycle of the input, the diode will get positive potential here, negative potential here. But since we are taking constant voltage model, the diode will not start conducting until the potential across it is greater than its knee voltage. That means until Vin becomes equal to the knee voltage of the diode, output will be 0. Let us show it over here in the graph. Once the input voltage becomes greater than the knee voltage, the diode becomes forward biased and we can model it to be a cell of potential equal to the knee voltage. So, the circuit model will look like this. Using KVL, we can write V output is going to be V input minus Vk. If we plot it on the graph, this is how it will look like. The output was 0 until Vin took a particular value that is equal to the knee voltage. Now, over here, input again becomes lower than the knee voltage. and hence the output becomes 0 there also. Let us show it on the graph like this. In the negative half cycle, the diode gets negative potential here and positive potential here. It is reverse biased, so it can be modeled as an open circuit. This is what we get. Since the circuit is open and no current will flow through the resistor, using Ohm's law, we can write V output is equal to 0. Let's mark it on the graph. So finally, the output looks like this. Let's get a better picture of the output. When we took the ideal diode model, the maximum value of the output is V0, which is the maximum value in the input. But when we take the constant voltage model, the maximum value we get in the output is V0 minus Vk, Vk being the knee voltage of the diode. Also, the output is 0 until the value of input becomes equal to the knee voltage. It can be referred to as the offset due to knee voltage. Let's try to find the average value of this output. Previously, when we took the ideal diode model, the average or the DC value was the peak divided by pi. Here also we can use the same expression because the wave still has the same shape. The only difference is peak is now V0 minus Vk. So we can write VDC is V0 minus Vk divided by pi, or 0.318 times V0 minus Vk. Here, if V0 or the maximum value of the input voltage is very much greater than the knee voltage of the diode, then we can write V0 minus Vk is approximately equal to V0. In that case, VDC will be approximately equal to V0 by pi, or 0.318 V0, just like in the ideal diode model. Let us now solve a problem. We have to sketch the output and determine its DC level. Diode is to be considered ideal. This is our circuit. This is the input. This looks exactly like a half-wave rectifier, except the diode is in the other direction. It has N here and P here. So in the positive half cycle of the input, diode will get positive here and negative here. It will be reverse biased. So we can model it as an open circuit. For 0 less than t by 2, this is how the circuit model will look like. Since the circuit is open, no current will pass through R, and therefore output is going to be equal to 0. To plot the output, let us take a graph. This is our input and this is our output corresponding to the input. For reference, I have still kept the ghost of our input over here. Now, for the positive half cycles, our diode will be in reverse bias and therefore the output is 0. Let us plot it on the graph. For the negative half cycles, the diode will get negative potential here and positive potential here. It will be forward biased, which means we can model it as a closed circuit. In that case, this is how the circuit model will look like. Here, whatever is the input is exactly seen across the resistor. So output is equal to the input. Let us plot it on the graph. Here the positive cycles are rectified and the negative cycles are still there. In this case, the DC value of the output will be negative of 0.318 multiplied by the peak value. Peak value, according to the question, is 20 volt. So we can write minus 0.318 multiplied by 20, which is minus 6.36 volt. Let's go to the next question. Here we have the same circuit, the same input, except the ideal diode is replaced by a silicon diode whose knee voltage is 0.7 volt. So here we have to use the constant voltage model. First, let's take a graph to plot our output. For reference, I have kept the ghost of our input here. Now, in the first half cycle, voltage is positive. So the diode will get positive potential here and negative potential here. It is reverse biased, so we can model it as an open circuit. Since the circuit is open, just like in the previous case, V output is going to be 0. Let us plot it on the graph. In the negative half cycle, diode will get negative potential here and positive potential here. But until the input voltage becomes at least 0.7, it will not start conducting. Let us show that on the graph like this. Now, when the magnitude of the input becomes greater than 0.7, the diode will start conducting. But since we are using the constant diode model, we have to model it using a cell with potential 0.7 volt. From KVL, we can write the output is going to be V in plus 0.7 volt. But between T by 2 and T, the input voltage is negative and we are adding plus 0.7 volt to it. So our output voltage will look something like this. According to the question, this is 20, so this will be minus 20. So this is going to be minus 20 plus 0.7. Instead of writing it like this, we can write it as negative of 20 minus 0.7. So when we took the ideal diode model, we got minus 20 here, and now we are getting minus of 20 minus 0.5. The magnitude decreased. Let's try to find the DC value or the average value. VDC is 0.318 multiplied by the peak value. Here it is negative, so we have a negative here, multiplied by 20 minus 0.7. And this comes out to be minus 6.14 volt. Let us compare this with what we got before. For an ideal diode, we got minus 6.36 volt. For a practical silicon diode, we got minus 6.14 volt. Therefore, if we calculate the drop in voltage, we get minus 6.36 minus 6.4 divided by the original value minus 6.36. If I want it in percentage, I'll multiply it with 100 and put percentage. This is approximately equal to 3.5 percentage. So for a practical diode, there is a drop of almost 3.5 percentage in this case. Let us take the same question again. But this time the difference is peak value of the input is not 20, it is 200 volt. Other than that, everything is the same. So let us draw the output for an ideal diode model and constant voltage model directly from the last two problems we solved. In the ideal diode model, instead of minus 20, I got minus 200. In the constant diode model, instead of minus of 20 minus 0.7, I got minus of 200 minus 0.7. Let us calculate the DC values in both cases. In the ideal diode model, it will be 0.318 multiplied by the peak value, which is minus 200. And this gives us negative 63.6 volt. Now, for a practical silicon diode, the DC value will come to be 0.318 multiplied by negative of 200 minus 0.7. And this comes out to be negative of 63.38 volt. The voltage dropped from 63.6 to 63.38. Let us calculate the drop in voltage in percentage. It will be minus 63.6 minus of minus 63.38 divided by the original value minus 63.6. To get it in percentage, I'll multiply it with 100. And this is approximately 0.35 percentage. When the peak value of the input voltage was 20 volt, we got a drop of 3.5 percentage. All we did here is increase the input voltage by 10 times. Here the peak is 200 volt and the drop decreased by 0.35 percentage. That is, the difference between an ideal case and a practical case is only 0.35 percentage. The only thing we had to do is increase the magnitude of the input voltage. The next concept we have to learn here is the peak inverse voltage or the peak reverse voltage. Consider this half-wave rectifier circuit and a sinusoidal input. Let us assume an ideal diode. When the input voltage is negative, it will get negative potential here and positive potential here. It will be reverse biased and we can model it as an open circuit. Since the circuit is open over here, current passing through the resistor will be 0. That means the potential across the resistor is 0. But we are applying the input potential over here. Since no potential is going to drop across the resistance R, all of the input will be dropped over here in the open circuit. Since V in is negative, negative potential will come here, positive will come here. Let's call the potential across the diode V. What is the maximum value V can get? V is equal to V input. So the maximum value V can get is the maximum value V in can get, which is V naught. Let us write this down. During the negative half cycle, the entire input voltage appears across the diode. We have seen the VI characteristics of a diode. It looks like this. If the inverse voltage becomes anything greater than the breakdown voltage, the diode gets damaged and the current through it becomes infinite. That means there is a maximum voltage a diode can withstand in the reverse bias condition without breaking down. That voltage is called the peak inverse voltage or the peak reverse voltage. We can denote it by PIV. So while designing a circuit, we have to make sure we are using the diodes that have PIV rating greater than or equal to the maximum value of input voltage that we are giving to it. So this is our half-wave rectifier circuit and this is the output that it gave us. Do you remember why we started this? Power was supplied to us in AC, but most of our electronic devices needed power in DC. So we decided we have to convert AC power into DC power somehow. But all the half-wave rectifier has given is an output that looks like this. This is not DC. So the circuit does not produce a useful output to us. This output is still varying considerably with time. So this cannot be used as a power supply to our electronic devices, which means we still have to do our work and modify this circuit so that it can be used as a power supply to our electronic devices. Let us try something. Let us add a smoothening capacitor instead of the resistor there. And let's take the output across the capacitor. Our input is still the sinusoidal voltage whose peak value is V0 and time period is T. First, consider when the input increases from 0 to its maximum value, that is from 0 to T by 4. Let us take the constant voltage model. From 0 to T by 4, input is positive. So our diode will get positive potential here and negative potential here. But we are taking the constant voltage model. So until the input voltage is greater than 0.7 in the case of a silicon diode, it will not start conducting. Let me take a graph with the ghost of our input so we can plot our output. Until the input voltage becomes equal to the knee voltage of the diode, it will not conduct. So until then, output is going to be 0. Let's plot it on the graph. After that, the diode will start conducting. Since we are taking the constant voltage model, we have to model it using a cell whose potential is the knee voltage of the diode. The circuit model will look like this. Now, when the input voltage increases from the knee voltage up to its maximum value, current will flow in this direction and our capacitor will get charged. Output voltage is taken across the capacitor, so it can be plotted like this. When V in reaches its peak value, what will be the peak value of the output? We can find that using KVL. We are giving V in here, we have a Vk here, and whatever comes over here will be the output. So we can write V output is equal to V in minus Vk. When V in has reached its peak, V output will be V0 minus Vk. Let us take the original circuit now. Assume that the input has reached over here and the value of V in is now V naught. Now the capacitor is also charged and it has a potential V naught minus Vk across it. After reaching the peak, the input voltage now has to decrease, which means ideally the potential across the capacitor should also decrease. But there is a problem with that. The capacitor got charged because of a current that was flowing in this direction. That means the electrons from this plate went to the plate over here. So this plate is now positively charged and this is now negatively charged. Now V in has to decrease from its peak value to 0. That means definitely the potential across the capacitance cannot increase because conservation of energy. We have to give energy to take energy. Since the input is decreasing, obviously the output cannot increase. So that is not an option. Now the question is, will the output decrease along with the input? V output is the voltage across the capacitor. It is V naught minus Vk. Now, if V output has to decrease, that means the capacitor has to discharge. For the capacitor to discharge, electrons from this plate have to go back to this plate. They will go like this. That means current flows in this direction. If current flows in this direction, that means current flows from the N side to the P side of the diode. Is that possible? No. So it is not possible for the capacitor to discharge. So that is also not an option. So the potential across the capacitor cannot increase. It cannot decrease. The only remaining option is it remains constant. So that is exactly what is going to happen. When the input decreases from its maximum value to 0, the capacitor will remain charged because it doesn't have a path to discharge, so the potential across it will remain the same. Now, let me give you another way of understanding the same concept. So we have a practical diode here because we are taking the constant voltage model. On the P side, it has V naught potential. On the N side, it has V naught minus Vk. Obviously, the potential on the N side is lesser than the potential on P side, so it is forward biased. It is a forward biased practical diode. I am going to model it as an ideal diode but with a cell of potential Vk in series to it. That makes sense, right? Let us do that. Now, this is an ideal diode. It will switch on and off at 0 voltage. Tell me what is the potential it gets on the P side. Here there is a V in, but here there is a minus Vk. So on the P side, the ideal diode is getting V naught minus Vk. What is the potential this ideal diode is getting on its N side? Its N side is directly connected to the capacitor. So whatever is the potential across the capacitor, that is what it is getting over here, and it is also V naught minus Vk. So right now, when the input is at its peak over here at this point, potential across this ideal diode on both its sides is V naught minus Vk. Now, assume that the input goes from the peak value to 0. That is, the input is decreasing. When the input decreases, the potential across the diode on the P side will decrease. This will become less than V naught minus Vk. On the N side, it will still be V naught minus Vk because the capacitor is not able to discharge anymore. So the potential of the P side is lesser than the potential of the N side, which means the diode is in reverse bias, which means we can model the diode as an open circuit. So we can write when T by 4 less than T by 2. That is when the input decreases from the maximum value to 0 at T by 2. This is how the circuit model will look like. The capacitor is completely charged, so it has V naught minus Vk across it. Diode is acting as an open circuit. So the output is going to be V0 minus Vk constantly. That is what we have plotted over here. Now the question is what happens between T by 2 to T. That is in the negative half cycle where the input is negative. When the input is negative, obviously the diode gets negative potential here, positive potential here. It is reverse biased. It has to be modeled as an open circuit, which will exactly look like this. So let us just modify this part. Instead of T by 2, I will write T, because from T by 4 to T, it is going to be exactly the same. Since the circuit is open, the capacitor will not be able to discharge. So it will have a constant potential across it, V0 minus Vk. V output will be equal to that. That is plotted on the graph. Again, let me ask you what happens if the next positive half cycle starts. To understand that, let's take the original circuit again. Right now, we are over here. V input is equal to 0. Capacitor is fully charged. It has a potential equal to V0 minus Vk. V output is V0 minus Vk. Again, let's do the same thing. This is a practical diode. I want to model it as an ideal diode with a cell of potential Vk with it. Now we are over here. Input is 0. This is Vk. So the potential the diode gets on the P side is minus Vk. On the N side, it is directly connected to the capacitor. So whatever is the potential across the capacitor, that is what it is getting here. It is V0 minus Vk. Now, the input is going to increase from 0 to maximum value V0. My question is, will the potential on the P side ever become greater than V0 minus Vk? No, even when Vin becomes its maximum value V0, whatever P side gets is V0 minus Vk. That is only equal to what it gets over here. So the potential that the diode gets on the P side is always going to be less than the potential it already has on the N side. So this diode is going to be reverse biased forever from now. The capacitor over here will never be able to discharge. Output that we got now is never going to change. It will be constantly V0 minus Vk. Let's make some space to write down the entire thing. From 0 to T by 4, the capacitor gets charged. That is from here to here. At T equal to T by 4, the capacitor is fully charged. After T by 4, the capacitor cannot charge anymore because the input voltage is decreasing, conservation of energy. Also, the capacitor cannot discharge. Why? If it has to discharge, then the current has to flow from the N side of the diode to the P side, which is not possible. Therefore, the only option left for us is that the capacitor voltage stays constant. And that is exactly what happens. Let us now solve a problem. Assuming ideal diode model, we have to plot the voltage across the diode as a function of time. This is our circuit and this is our input. The input is sinusoidal. Let's take a better look at our circuit for analysis. Let us also take two graphs to plot the output and the voltage across the diode. Let's mark the potential across the diode Vd. Now consider the input from 0 to T by 4. Input goes from 0 to its maximum value. Input is positive, so the diode will get positive potential here and negative potential here. It is going to be forward biased, which means we can model it as a closed circuit. In this case, whatever is given at the input is exactly seen across the capacitor. And we are taking the output across the capacitor, so output is going to be equal to input. Let us plot it on the graph like this. Also during this time, diode is acting as a closed circuit, which means the potential across it Vd is equal to 0. Let us plot that also in the graph. During this time, the capacitor gets charged. It will have positive potential here and negative potential here. V output is equal to V input. So at T by 4, V output is equal to V naught. Now let's see what happens to the diode after this. After T by 4, the input has to decrease from its maximum value to 0. When input is decreasing, obviously the output cannot increase because of conservation of energy. My question is, will output decrease along with the input? See, we have taken the output across the capacitor. So output decreases means voltage across the capacitor decreases. Voltage across the capacitor decreases means the capacitor is discharging. The capacitor has positive charges on this plate and negative charges on this plate. So if it has to discharge, that means the extra electrons on this plate should flow to the other plate, which means current has to flow from this plate to this plate. If current is flowing in this direction, that means current is flowing from the N side of the diode to the P side of the diode, which is impossible. So the capacitor cannot discharge. That means the potential across it cannot decrease. That means V output cannot decrease. So from T by 4 to T by 2, even when the input is decreasing from its maximum value to 0, output will remain V naught. Let's plot it on the graph. Now let me give you a different way of understanding this. At T by 4, capacitor has completely charged and it has a potential V naught across it. Also at T by 4, input voltage is its maximum. It is equal to V naught. So V in is V naught, V out is also V naught. According to the diode, on the P side it is getting V naught. On the N side also it is getting V naught. Now from T by 4 to T by 2, input has to decrease from its maximum value to 0. That is, during this time, V input is going to be less than V naught. Will the output change? No, because the capacitor does not have a path to discharge. V out is going to be still V naught. So, according to the diode, on the N side it is still getting V naught, but on the P side, now it is getting less than V naught. P side of the diode is at a lower potential compared to the N side. That makes the diode reverse biased and we can replace it as an open circuit. Since the circuit is open, the capacitor cannot discharge, so the potential across it is going to be constantly V naught. We already plotted that on the graph. Now, how about the next half cycle where the potential is negative? See, in the negative half cycle, the diode gets negative here, positive here. It is reverse biased anyways, so we can again model it as an open circuit. So from T by 2 to T also, output is going to be constantly V naught. Let's mark it on the graph. Let's bring back our diode again to understand what happens in the next cycle. After T, the input goes from 0 to its maximum value, then decreases to 0, again decreases to minus V naught, and then goes to 0, then goes to plus V naught. It goes on like that. The maximum value input can take is V naught. That means the P side of the diode will always have a potential that is less than or equal to V naught. But on the N side, it already has V naught from the capacitor. The P side can never have a potential that is greater than V naught. So we can see that the P side of the diode is never going to have a higher potential than that it has at the N side. This means the diode is going to be reverse biased forever. So from now, we can simply replace it by an open circuit. Again, the capacitor does not have a path to discharge, so the output is going to be constantly at V naught. Let's mark it on the graph. The output voltage is going to be V naught forever. So from the output graph, we can see that after T by 4, when the capacitor gets completely charged, the diode is forever in reverse bias. The diode is forever modeled by an open circuit. To find the potential across the open circuit VD, let us use KVL. We are giving the input here. We have a drop across the diode. We have a drop across the capacitor. So the input given is going to be drop across the diode plus drop across the capacitor. Drop across the capacitor is V output and V output is equal to V naught. So we can write VD plus V naught. From here we get VD, or the voltage across the diode, is input voltage minus a constant which is V naught. Input voltage looks like this. If you subtract a constant V naught from it, the entire waveform will be shifted downwards by that much. So we will get something that looks like this. Since T equals T by 4, the diode is a closed circuit and the capacitor is charging. During that time, potential across the diode is 0 because it is a closed circuit. After that, the potential across the diode is input voltage minus V naught. So when input voltage is V naught, diode voltage will be V naught minus V naught, that is 0. When input voltage is 0, diode voltage will be 0 minus V naught, that is minus V naught. When input voltage is minus V naught, diode voltage will be minus V naught, that is minus 2 V naught. Let us solve another problem. Assume ideal diode model, plot the voltage across the diode D as a function of time. Input is still the same sinusoidal input. Circuit is also the same except the diode is in the other direction now. Let's get a closer look of the circuit for the analysis. Let us also take two graphs to plot the output and the voltage across the diode. For reference, I have kept the ghost of our input on both of these graphs. Now, in the first half cycle of the input, voltage is positive. So the diode will get positive potential here and negative potential here. It is reverse biased, so we can replace it using an open circuit. The capacitor is not charged, so the potential across it is 0. Therefore, during this time, V output is also 0. Let us plot it on the graph. Let's mark the potential across the diode as VD. Diode is modeled to be an open circuit, so the entire input voltage is going to drop across the diode. VD is going to be equal to V in during this time. Let's plot it on the graph. Let's bring back the diode to see what happens after that. From T by 2 to 3T by 4, input voltage goes from 0 to minus V naught. It is negative. So the diode will get negative potential here and positive potential here. It will be forward biased. We can model it as a closed circuit. During this time, the entire input will be dropped across the capacitor. So V output will be equal to V input. Let's show it on the graph. The diode is modeled as a closed circuit because it is in forward biased. So the potential across it, VD, is going to be 0 during this time. Let's plot that also in the graph. By 3T by 4, the capacitor will get charged by a potential minus V naught. So it will have negative charges on this plate and positive charges on this plate. To see what happens after this, let us bring back the diode in the circuit. At 3T by 4, potential across the capacitor is minus V naught. So V out is minus V naught. After that, the input voltage goes from minus V naught to 0 and then to plus V naught and then again to 0. Basically, V input is going to be always greater than minus V naught. So let's write V input is going to be greater than or equal to minus V naught. The same situation again arises. When V input increases, does V output also increase? No. V output is minus V naught now. It is the maximum negative it can reach. If it has to become less negative, that means the capacitor has to discharge. The capacitor has negative charges here and positive charges here. If it has to discharge, electrons have to go from here to here. Current has to go from here to here. If current is flowing in this direction, that means it is flowing from the N side of the diode to the P side of the diode, which is not possible. So our capacitor cannot discharge. It obviously cannot charge anymore because that will be against conservation of energy. So the only option left is it will remain the same. V output will remain minus V naught. So on the P side, the diode will have minus V naught. On the N side, it can have potential that is always greater than or equal to minus V naught. That means the N side of the diode will never be more negative than the P side. So this diode from now is always going to be reverse biased and we can model it as an open circuit. Let us conclude. After 3T by 4, the diode is going to be reverse biased forever. The circuit is going to be open forever. Capacitor does not have a pathway to discharge, so the voltage across it is going to be constant forever. Our output voltage is going to be minus V naught forever. So let us plot it on the graph like this. How about the potential across the diode? Input is given over here. Some of it will be dropped across the diode as Vd, and across the capacitor we have minus V naught. V input will be dropped across the diode and the capacitor. But voltage across the capacitor is minus V naught, so we can write Vd minus V naught. This gives us Vd, or the potential across the diode, is input voltage plus a constant V naught. V naught is the peak value of our input. So after 3T by 4, Vd is going to be V input plus V naught. After 3T by 4, V input looks like this. We want V input plus V naught. So the entire waveform will shift upwards by V naught units. We will get something that looks like this. When input is minus V naught, Vd is minus V naught plus V naught, that is 0. When input is 0, Vd is 0 plus V naught, that is plus V naught. When input is V naught, Vd will be V naught plus V naught, that is 2V naught. So voltage across the diode for the first half cycle of the input is equal to the input. After that, for a quarter of the cycle, it is 0. After that, it is V input plus V naught. So it goes on like this. So when we took the output across a resistor, our output looked like this. The circuit did rectify the negative half cycle, but the output is still oscillating. On the other hand, when we took the output across a capacitor, we actually got a unidirectional constant voltage, which is what we wanted in the first place. We had to get a DC output from an AC input. Somehow we have got it here. Now, what are we going to do with this? We have to use this as a voltage supply to some electronic device. For example, we are trying to charge your laptop. The laptop in this case will be the load. In this case, we can model it as a load resistor. So, in a more realistic point of view, we will have to add a load resistor to this circuit. So, let us see what happens when the circuit is connected to a load. Without the load, When the capacitor got completely charged and the diode became reverse biased, the capacitor did not have any path to discharge anymore. That is why we got a constant voltage after that. But when the load is connected, the capacitor has a path to discharge even when the diode is replaced by an open circuit. It will discharge through the resistor. Let us take this circuit as an example. Assume that the capacitor got completely charged. It has positive potential here and a negative potential here. Without the load, if the capacitor had to discharge, the current has to flow like this. That is from the N side of the diode to the P side, which is impossible. So the capacitor was not able to discharge. Now, since there is a load resistor, the electrons from this plate will be able to flow through the resistor to the other plate. Current will be flowing from this plate through the resistor to the other plate, and the capacitor will be able to discharge. Before we move on and see how the output voltage will look like, there is a small concept we have to learn. Assume that the capacitor got completely charged, diode is now in reverse bias forever, and it is replaced as an open circuit. Now, since the load resistor is here, capacitor is going to discharge through the resistor. Now, if V0 is the potential across the fully charged capacitor, we have learned that the potential across the capacitor as a function of time can be written as V0 e raised to minus t by tau, tau being the time constant RC. We learned this in the previous video. Output voltage is taken across the capacitor, so we can write V output is equal to V0 e raised to minus t by tau. If we plot this on a graph, this is how it will look like. At t equal to 0, V output will be V0 multiplied by e raised to 0, that is equal to V0. So you can see in the graph at t equal to 0, output is V0. After that, it exponentially decreases. Let us do a small approximation. Consider t is very much less than t. That means the time constant of the RC circuit is really high. Obviously, we cannot do anything about the load resistor because the load is the device we are trying to charge. It is fixed. So we'll have to increase the capacitance of our capacitor, which is in our hands. We are designing the half-wave rectifier. So we can also say the capacitance is really high. Under this condition, let us take V output. V output is V0 e raised to minus t by tau. Using binomial expansion, e raised to minus x can be written as 1 minus x plus x square by 2 factorial minus x cube by 3 factorial plus etc. Infinite terms will be there. Here we have e raised to minus t by tau. So x is t by tau. So x is t by tau. We have taken the condition t is very much less than tau. So t by tau is going to be very much less than 1. T by tau is very much less than 1 or x is very much less than 1. Since x is very much smaller than 1, its higher powers like x square and x cube can be considered to be 0. So we can write since x is very small, e raised to minus x is approximately equal to 1 minus x. Or e raised to minus t by tau can be approximately equal to 1 minus t by tau. Let us substitute that here. V output is V0 multiplied by 1 minus t divided by tau. That is V0 minus V0 t divided by tau. Or minus V0 by tau t plus V0. This is V out. I want to plot V output versus time. I have the equation V output is minus V0 by tau multiplied by t plus V0. I can see that this is of the form y equals mx plus c. This is the equation for a straight line. On the y-axis, I have taken V output. On the x-axis, I have taken T. M is the slope of the graph. Correspondingly, here I have minus V naught by tau. C is the y-intercept. Correspondingly, here it is V naught. So if we plot this, this is how the graph will look like. Its y-intercept is V naught and it has a negative slope. The slope will be equal to minus V naught divided by tau. Let me conclude the approximation. If the time constant is really large, that means the capacitance is really large, then the output can be approximated to be linearly decreasing rather than exponentially decreasing. Keeping this concept in mind, let us try to analyze a half-wave rectifier with both capacitor and the load resistor. First, we'll take the ideal diode model. Let's take a graph to plot the output. Initially, when the input goes from 0 to its maximum value, diode will get positive potential here, negative potential here. It will be forward biased and we can replace it by a closed circuit. During this time, the entire input will be dropped across the capacitor and the resistor in parallel. So the output is going to be equal to the input. Let us plot it on the graph. Now the input has the maximum value V0 and the capacitor is charged. It has positive charge on this plate and negative charge on this plate. Let's bring back the diode to see what happens next. Potential across the capacitor is V0. V input is now going to decrease from the maximum value to 0. That means on the P side, the diode will have potential that is less than V0. But on the N side, it has V0 from the capacitor. So the diode is going to have less potential on the P side, more potential on the N side. It will be reverse biased. We can replace it by an open circuit. Earlier, without the load resistor, the capacitor did not have a path to discharge. So the potential across it remained constant and the output remained constant. But now, capacitor can actually discharge through the resistor. If the time constant is really high, it can discharge linearly. If the time constant is small, it can discharge exponentially. To consider both cases, let me duplicate this. In the first case, let us consider tau or the time constant is really large. Time constant is RC, so RC is really large. But the value of R is not in our hands. R is the load resistor. It is the laptop or the mobile phone or whatever device you're trying to charge. But we designed the half-wave rectifier, so we can decide how much C is. So basically, in the first case, C is really high. Because of the high capacitance, the capacitor will discharge very slowly. In the second case, tau is smaller. RC is smaller. Again, the value of R is not in our hands, so let us assume capacitance is smaller. In that case, the capacitor will discharge really fast and the discharging will be exponential. When the capacitor discharges, in the first case, the voltage will drop linearly. In the second case, it will be exponential. In the first case, capacitor discharges slow, so even after one time period, there is still some potential across the capacitor. In the second case, the capacitor discharges faster, so over here itself, the potential across the capacitor has become 0. To see what happens next, let us bring back our diode over here. Concentrate on the first case where the capacitance is really high, capacitor is discharging slow, and the voltage across the capacitor is decreasing linearly. Voltage across the capacitor keeps decreasing like this, and at this particular time, voltage across the capacitor is equal to the input. According to the diode, on the P side, potential is provided by the input. On the N side, it is provided by the capacitor. At this particular time, they are equal. So the diode has equal potential on the P side and on the N side. What happens next? Capacitor voltage is supposed to decrease, but input voltage is increasing. So the diode has more potential on the P side, less potential on the N side, which means the diode will go to forward bias region and we can model it by a closed circuit now. Now for once again, V input is directly connected across the capacitor. So V output which is taken across the capacitor is going to be equal to the V input. We can show it on the graph like this. At this time, the capacitor will get completely charged. It will have a potential V0 across it. V input is only decreasing after that. So according to the diode, it has V0 on this side and less than V0 on this side. The diode will go to reverse bias and it will become an open circuit. Capacitor will again try to discharge through the resistor. And since we have large C, capacitor will be discharging linearly. We can plot it on the graph like this. This keeps happening every cycle. In the second case also same thing happens. The only difference is discharging is exponential. So the drop in voltage across the capacitor is also exponential. The voltage drops exponentially like this. It becomes 0. But at this point, voltage across the capacitor is equal to the input voltage. So on both sides of the diode, we have equal potential, that is 0. After that, voltage across the capacitor tries to be 0. Input increases from 0 to its maximum value. That means the diode will go to forward bias region and the capacitor will charge again. Once the capacitor is completely charged, the diode will go back to reverse bias region and the capacitor will discharge through the resistor once again. Since the capacitance is very small and it is discharging faster, drop in potential will be exponential. So it will look like this. Obviously, the first one gives us a better output than the second one. So we have to make sure we are using large C and that our time constant is really large, so that the capacitor discharges low enough, making the fluctuations in the output less. This is how the output looks like. Is it exactly DC? No, there are still some fluctuations. We call them the ripple. Even though there are variations, the output is still better than the output when we did not have a capacitor. When we did not have a capacitor, output looked like this. Obviously, this is much better than that. The capacitor has smoothened our output a little bit. Because of that, we call the capacitor a smoothening capacitor or a filter capacitor. We have one ripple in every cycle of the input. So we can say the ripple frequency will be equal to the input frequency. Let us now plot the two outputs for constant diode model. When the capacitance is really large, this is how it will look like. When the capacitance is really small, this is how it will look like. The only difference here is when V input first starts from 0 to its maximum value, the diode will not immediately turn on. It needs the input to at least be equal to the knee voltage so that it will be turned on and the capacitor can start charging. You can see that over here in the graph. Until the input becomes equal to Vk, output is 0. The same thing happens in this case also. After that, the diode will turn on and the capacitor starts charging. The maximum voltage across the capacitor in this case will be V0 minus Vk. Once the capacitor is completely charged, the diode will go to reverse bias and the capacitor will start discharging through the resistor. In the first case, the discharge is linear, so the drop in voltage is also linear. In the second case, the discharge is exponential, so the drop in voltage is also exponential. Concentrate on the first case. Voltage across the capacitor keeps decreasing. It goes on like that. At this particular point, this is the potential across the capacitor and this is the input voltage. Input voltage is higher than the voltage across the capacitor. Assume that the difference between them is equal to the knee voltage Vk. After this, the input voltage is increasing above Vk. The difference between the capacitor voltage and the input voltage is increasing from Vk, which means the diode will become forward biased again, which means the capacitor will start charging again until it reaches the maximum value, after which diode will go back to reverse bias region and capacitor will discharge again. This keeps happening every cycle. On the other hand, when capacitance is really small, capacitor discharges faster. It has already become zero over here. So at this particular time, voltage across the capacitor is zero. Input voltage is this much. Let us assume that the difference between them is the knee voltage. After that, the input is increasing, so the difference between them will be more than Vk, which means the diode will go back to forward bias region. Capacitor will start charging again. Once it is completely charged, it again discharges exponentially. This keeps on happening cycle after cycle. Let us concentrate only on the case where capacitance is really large, time constant is really large, capacitor is discharging really slow, and because of all that, the drop in output voltage is linear. Here, this is the maximum potential the output is taking. This is the minimum value it is taking. The difference between them is called ripple voltage. Obviously, you can see initially the output is 0, so obviously that should be the minimum value. Well, forget about that part. Only consider the output after the capacitor is completely charged. That is from here. We did the entire thing to convert an AC voltage to a DC voltage. So ideally, we needed the output to look like this. Obviously, it does not look like that. It has ripples in it. So we want the ripples to be as small as possible. That means we want the ripple voltage to be as small as possible. Typically, the amplitude of the ripple must be below 5 to 10% of the peak value of the input. So while we are designing the half-wave rectifier, if the maximum current drawn by the load is known, then the value of the capacitance is chosen such that it is large enough to yield an acceptable ripple. Acceptable value of ripple is below 5 to 10% of the peak value of our input. Let us do the math of it. I have marked 2 points T1 and T2. The discharge is happening between T1 and T2. The maximum voltage across the capacitor is over here. It is V0 minus Vk. From there, it is decreasing. Since we are taking the linear model, we can write V output is the maximum value, which is V0 minus Vk, multiplied by 1 minus T by tau. This is when time is between T1 and T2. This is equal to V0 minus Vk minus of V0 minus Vk divided by tau multiplied by T. Instead of tau, we can write RC. We need to find an expression for the ripple voltage VR. From the graph, we can see VR is this value minus this value. This is the maximum potential across the capacitor. It is V0 minus Vk. So VR is V0 minus Vk minus of whatever is the potential across the capacitor at time being T2. So I'm going to write V out at T equals T2. Over here, we already have V output as a function of time. V output is V0 minus Vk minus of V0 minus Vk by Rc multiplied by T. Now, to get the output voltage at T equal to T2, I should simply replace T by T2, right? Wrong. See, this equation shows the output voltage only between T1 to T2, where the discharge is happening and the decrease in the voltage is linear. So we are starting at T1 and going to T2. So when we reach T2, the time passed is this much. This is T2 minus T1. So I have to replace T here by T2 minus T1. Then I will get the output voltage at T equal to T2. So ripple voltage is V0 minus Vk minus of output voltage at T equal to T2. It is V0 minus Vk minus V0 minus Vk divided by Rc multiplied by T2 minus T1. Again, I took T2 minus T1 because we started here. This is our initial point. And then we reached here. This is our final point. So between the final point and the initial point, time that has passed is this much. T2 minus T1. Now we can write VR as V0 minus Vk minus V0 minus Vk plus V0 minus Vk divided by Rc multiplied by T2 minus T1. These two will cancel each other. So ripple voltage is V0 minus Vk divided by Rc multiplied by T2 minus T1. Now T2 minus T1 is this much. T1 is the middle of the first half cycle. So from T1 to this point, we have one time period. T2 is a little behind that. So T1 to T2 is a little bit less than one time period. But the time between T2 and this point is very small. So we can say T2 minus T1 is approximately equal to the time period. In that case, we can write VR is approximately equal to V0 minus Vk divided by Rc. T2 minus T1, we will write T. Time period can be written as 1 by frequency. Using that, we can write ripple voltage is approximately equal to V0 minus Vk divided by Rcf. Vr is the ripple voltage, V0 is the peak voltage of the input, Vk is the knee voltage of the diode, R is the resistance of the load, C is the capacitance of our capacitor, F is the frequency of our input. Now assume that instead of the resistance of the load, you know the current that the load draws. In that case, V0 minus Vk divided by R using Ohm's law can be considered as the current drawn by the load. And you can write VR is equal to current drawn by the load divided by Cf. Let us now solve a problem. We have a transformer that is converting a 110 volt 60 Hz line voltage to a peak to peak swing of 9 volt. There is a half-wave rectifier that is following the transformer. The half-wave rectifier supplies the power to a laptop which consumes an average power of 25 watt with a supply of 3.125. That means when the supply is 3.125 volt, laptop consumes 25 watt of power. We have to find the minimum value of the capacitor that maintains the ripple below 0.1 volt. It is given the knee voltage is 0.7 volt. So basically we have to decide the half-wave rectifier that will work according to the requirements. Here the half-wave rectifier follows a transformer. So let me draw the circuit. The original input is 110 volt 60 Hz. Transformer steps it down to 9 volt. Transformer does not do anything to the frequency of the signal, so it will still have 60 Hz frequency. So input to our half-wave rectifier has a peak-to-peak voltage of 9 volt and frequency is 60 Hz. 9 volt is the peak-to-peak voltage. That is from the highest point to the lowest point. So the maximum value of input V0 will be 9 divided by 2, 4.5 volt. It is given that the laptop consumes a power of 25 watt if the power supplied is 3.125 volt. From this information, we can find the resistance of the laptop. Power is given by V square divided by R. So the resistance R will be V square divided by power. That is 3.125 squared divided by 25. And this is approximately equal to 0.4 ohm. Therefore, our load resistance is 0.4 ohm. Now, let's write the expression for the ripple voltage. VR is V0 minus Vk divided by RCF. We need to design the half-wave rectifier such that the ripple voltage is below 0.1 volt. So let us assume the extreme case where the ripple voltage is equal to 0.1 volt. We have to find out the value of C. C will be V0 minus Vk divided by VR RF. Giving values, V0 is 4.5 minus Vk is 0.7 divided by the maximum value VR can take is 0.1 multiplied by resistance of the load is 0.4. Frequency of the input is 60 Hz. This is approximately equal to 1.56 farad. To keep the ripple below 0.1 volt, we have to use a capacitor with capacitance greater than 1.56 farad. This is actually a very huge value for a capacitor. We usually take it in microfarads. So when this happens, the designer might have to make a choice whether to compromise on ripple to reduce the costs or stick with a larger capacitance for a cleaner output. It all comes down to the specific priorities of the design. So that's all about it for today. See you in the next video. And don't forget to subscribe.